Every time you open a map app or load a web page, you rely on systems evaluating millions of intersecting paths in fractions of a second. The core mathematical challenge driving all of these systems is identical: finding the single most efficient route between a starting location and a destination. This diagram shows a simplified model. If you need to travel from Delhi to Mumbai, and you are presented with 3 routes, 1,400, 1,500, and 1,300 kilometers, human intuition immediately identifies the shortest option. But explode this out to a real-world scale. A computer mapping a route across a country isn't looking at 3 lines. It navigates a chaotic web of thousands of interconnected intersections. Checking every conceivable sequence of roads one by one would take a computer centuries. To make modern navigation possible, we need a mathematical shortcut that discards the bad routes instantly. The mathematical solution to this problem is Dijkstra's algorithm. Before we can track exactly how it operates, we must construct the strict mathematical architecture and vocabulary that allows a computer to perceive distance in the first place. The most basic unit of travel in computer science is called a path. This diagram shows exactly what that looks like: a sequence of connected vertices moving sequentially from node A to B to C and finally D. To make this useful for calculation, we assign a numerical value to each connection. This transforms our basic model into a weighted graph. These weights are abstractions. Depending on what you are measuring, they can represent physical distance in kilometers, the cost of a flight in dollars, or network delay in milliseconds. When an algorithm evaluates a route, it relies entirely on a metric called path cost. We calculate this by simply adding the edge weights along our route. Traveling from A to C means adding 5 and 3, giving us a total path cost of 8. For any algorithm to begin evaluating these costs, it requires an absolute non-negotiable starting point, known as the source vertex. By locking in node A as our origin, the algorithm has a 0 point from which all distances are measured. The target endpoint of the journey, in this case node D, is defined as the destination vertex. Without this strict anatomy of nodes, edges, and quantifiable weights, a computer has no objective way to evaluate whether one route is superior to another. Now that we have a measurable environment, we can define the specific problem Dijkstra's algorithm is built to solve. It is formally known as the single source shortest path problem. The constraint here is literal. The algorithm calculates routes radiating outward from exactly one fixed origin point. It never evaluates paths starting from multiple locations at once. And it doesn't stop once it finds a single destination. It continues mapping the optimal route from that origin to every single node in the entire network simultaneously. This behavior frequently causes students to confuse Dijkstra's algorithm with minimum spanning tree algorithms, like prims or Kruskals. To understand why they are completely distinct, let's directly compare the two side by side. This animation on the left shows a minimum spanning tree. Its objective is to connect every node in the system using the least amount of total material, whether that's physical copper wire or highway asphalt. On the right, Dijkstra's calculation prioritizes something else entirely: the absolute fastest travel time for an individual moving from the center out to any specific point. To achieve the cheapest overall infrastructure cost, a minimum spanning tree will often force a traveler to take a long, winding detour. Dijkstra completely ignores total infrastructure cost. It strictly prioritizes direct, selfish travel time for a single packet of data or a single car. Minimum spanning tree algorithms are for the engineers laying down the network. Dijkstra's algorithm is for the navigators traveling through it. To execute this search efficiently, Dijkstra relies on a strategy known as the greedy method. The defining characteristic of a greedy algorithm is that it constantly evaluates its current options, permanently locks in the absolute best choice at that exact moment, and never reverses that decision. When the algorithm first initializes, it is entirely blind to the layout of the network beyond its immediate origin. We can track this initial state using this simple distance table. Because it is already at the starting node, the source distance is recorded as 0. Since it hasn't mapped the rest of the grid yet, it mathematically assumes every other destination is infinitely far away. From there, it scans the connecting edges, strictly selects the unvisited vertex with the smallest known distance, and declares that path permanent. This greedy logic is highly efficient, but it has a specific vulnerability. It demands strict mathematical conditions to function accurately. First, the graph must be fully connected. If a node physically cannot be reached from the source, its distance value will permanently remain at infinity. Second, and crucially, all edge weights must be strictly non-negative. In reality, a road cannot have a physical distance of -10 kilometers. Dijkstra's greedy logic operates on the assumption that adding more edges to a route will always increase the total path cost. If negative weights were present, the algorithm might lock in a seemingly optimal path early on, completely missing a longer route that mathematically subtracts distance later down the line. It corrupts the entire methodology. We have now constructed the foundational rules required to make shortest path calculations possible. A helpful memory trick to retain the exact parameters of Dijkstra's problem statement is the acronym SSAM. It requires one source to find the shortest path to all vertices by calculating the minimum distance. It relies entirely on greedy logic, meaning it permanently locks in decisions step by step and strictly requires non-negative edge weights to remain accurate. And its sole purpose is radial navigation outward from a specific point, completely separate from the goals of spanning trees. When these mathematical rules operate flawlessly at scale, they form the invisible backbone of global routing and satellite navigation. You now possess the complete architectural framework of the algorithm. In the next lesson, we will apply this strict theory, utilizing a min-heap priority queue to execute a complete step-by-step mathematical dry run, because understanding the absolute rules of the grid is the prerequisite to mastering how to navigate it.